So 3i Atlas recently passed its closest point to Earth, and we just got some massive updates today about the object's actual size, which is yet another anomaly because the new calculations completely contradict previous measurements we've been seeing for months. So on December 23rd, scientists published brand new calculations revealing how big 3i Atlas actually is. They measured the size based on what we call the non-gravitational acceleration. This is the tiny push an object gets when gas shoots off the surface, creating a rocket effect. Now, the object's non-gravitational acceleration was measured at 89.3 times 10 powers, 9 astronomical units per day squared. This means that every day, 3i Atlas moves 13 km per day faster than the day before. To put that in perspective, this is only 1/5,000,000th of Earth's gravity, so incredibly tiny. But with precision tracking from hundreds of observatories, scientists can detect even that small of a push. Now, here's how scientists turn that into a size measurement. The strength of that push depends on two things: how much gas is escaping per second and how fast that escaping gas is moving. Well, the James Webb Space Telescope measured both. The gas is escaping at roughly 1,600 km per hour, and the total mass loss rate is about 150 kilos per second. So scientists then asked the key question: what size comet would make these two measurements consistent with each other? Well, math tells us that the diameter must be 1 kilometers, or, to be more exact, somewhere between 800 and 1,000 meters, assuming typical comet properties. Now, comets are usually not very dense. Typical comet density is around 500 kilos per cubic meter, which is about half the density of water. They are fluffy with lots of empty space between ice chunks. So, using these new measurements, I calculated that 3i Atlas weighs about 260 billion kilograms. That's 1 kilometer wide and weighing about 260 billion kilograms. This is what 3i Atlas actually is based on direct calculations of its acceleration and outgassing. But here's where everything breaks down. Earlier this year, between May and September, different scientists were tracking 3i Atlas before it got close to the Sun. They used data from over 230 observatories worldwide with position tracking accurate to 0.028 arcseconds. To put that in perspective, that is like being able to spot a coin from over 100 kilometers away. Incredibly precise. Well, during that entire 5-month period, they could not detect any non-gravitational acceleration at all. Now you might think, okay, they just were not looking hard enough, but their detection limit was about 300 times more sensitive than the recent measurements. So if there was even a tiny push happening, they absolutely should have seen it. So here is what that means. If the acceleration was truly below that detection threshold, then the object must be much more massive than 260 billion kilograms. Because weaker acceleration means you need more mass to produce the same outgassing force. Harvard scientist Avi Loeb previously calculated that if acceleration was below the detection limit, 3i Atlas must weigh at least 33 trillion kilograms. This is 33 billion tons, and at normal comet density, that means a diameter of at least 5 kilometers, which is the size we've been told for months. So now we have a massive contradiction. The new December calculation says 1 kilometer and 260 billion kilometers. The May through September detection limits say at least 5 kilometers and at least 33 trillion kilograms. That is a 5 times size difference and a 120 times mass difference. Image comparing the mass and volume differences between 1 kilometer and 5 kilometer diameter spheres. So I have a few theories on what could be causing this size difference in measurements. The first thing to know is that NASA has been revising the acceleration measurements since the first measurement papers were published. The non-gravitational acceleration value has been downsized multiple times as scientists refine their models and account for uncertainties in the telescope data. If the true acceleration is lower than what was first used, then the diameter calculation would be larger. This could help bridge the gap between 1 kilometer and 5 kilometers. The second possible factor is mass loss over time. The comet was probably heavier back then before it started shedding billions of kilograms of ice and dust. Between May and September, 3I Atlas was far from the Sun and relatively cold. By October, it was near perihelion, getting hammered with solar energy and losing massive amounts of material. If the comet weighed more in May through September than during the recent measurements, that would explain why the earlier lower bound is higher. The third possibility is asymmetric outgassing combined with rotation. If gas is shooting out from highly active regions on one side of the comet, the rocket effect depends entirely on which direction those jets are pointing. During May through September, the active regions might have been oriented so the thrust was perpendicular to the orbit. That would create acceleration that does not show up in position tracking along the orbital path. Then, in October, as the comet rotated and heated up differently, those jets could have pointed in a direction that produced measurable acceleration along the trajectory. This is actually pretty common in comets. We see it all the time with objects in our solar system. The fourth factor is the model assumptions themselves. The calculations assume a certain density, around 500 kilodon per cubic meter, and a certain level of outgassing symmetry. Small changes in these assumptions can significantly affect the diameter result. If 3I Atlas has slightly higher density than typical comets, or if the jets are more asymmetric than the models account for, the 1 kilometer measurement could shift upward while the 5 kilometer lower bound could shift downward. They might actually meet somewhere in the middle. The bottom line is, this is an active area of research. New observations are coming in, the models are being refined, and the acceleration values are being updated. Scientists are working to figure out which combination of these factors explains what we are seeing. This is somewhat of a normal scientific process. Measurements get revised, models get improved, and understanding evolves. What makes this particularly challenging is that 3I Atlas is an interstellar object. We have never studied a comet from another star system this closely before. Image showing the hyperbolic trajectory of an interstellar object through our solar system. So some of the assumptions we make based on solar system comets might not apply perfectly here. The chemistry is different, the age is different, and the thermal history is different. Scientists are learning in real time how to interpret data from an object that formed billions of years ago in a completely different stellar environment. Leave a comment with your thoughts and theories about what's going on with 3I Atlas, and please drop me a like and hype if you enjoyed the video. God bless you, and I wish you a very good day.